who's an assistant professor at Purdue in mechanical engineering. So I've known Kevin since we were a grad student at Cornell, working on building control. We have a lot of mutual research interests. And then he did a postdoc and TV for Purdue 3 years ago.
That's right.
2 years ago.
Yeah.
Okay. Thank you.
All right. Well, thank you for the introduction. Thanks everybody for being here. A really great visit to Michigan so far. Lots of exciting conversations with collaborators and future collaborators. So it's a real pleasure to be here. Today, I'm going to talk about control opportunities in electrified housing, and I'll talk a little bit about what that means. But basically, electrification of a home doesn't mean what it used to in like the 1930s, when there was a big push to actually bring power lines out to people's homes in rural areas. Kind of in the modern context, it means swapping fossil fuel equipment in our homes, things like furnaces and stoves and water heaters over to electricity. And so we'll talk about kind of some control problems that I've studied in that space. Also, I'll talk a little bit about kind of motivation for the work as well. I won't go into maybe as much detail about the sort of algorithms as one might expect in a control seminar. I'll kind of sketch out some new problems and talk about some sort of first cut approaches that we're taking to those problems. But it's actually some aspects of the research area are pretty novel. So there's still a lot of room for innovation there. So we'll start by talking about generally climate change and how electrification fits into that picture of climate change. Then we'll talk a little bit about 2 experiments, field experiments that I've done in a test house that's near Purdue's campus where I work. My graduate students actually live in the house and coordinate the research and experiments that we do there. So one that's more about kind of energy efficiency for heating and cooling equipment, and then one is about protecting the electrical infrastructure, the wiring and the panels within the house. And then I'll wrap up just by talking about a couple of future directions, kind of proposals and projects and areas that I think it would be fun to move into. So humans have changed the climate already, and we're sort of seeing just the leading edge of the effects of climate change, which will continue for generations to come. This is a graph, time on the x-axis, and then 2 y-axes here. One of them is the number of events that cost people more than $1 billion in terms of damages. And the other is the cost of those events, the sort of time averaged cost of the events. And so you can see that starting around 2005, there was a really significant increase in these, the number and the severity of these events. So these are things like extreme weather, severe storms, hurricanes, as well as heat waves and cold snaps and droughts and all the other kind of weather effects that we're seeing. And somewhat ironically, the National Oceanic and Atmospheric Administration, the scientists who work at NOAA, who maintain this database, they were hit in their headquarters in Asheville, North Carolina, by Hurricane Helene. So the people who were working on the billion-dollar disasters actually got hit by a billion-dollar natural disaster. So I think we can think of climate change. There's many ways to think about it, but I think one for a controls community is to think about it as basically a problem of sequential decision-making under deep uncertainty. So something you could maybe think of as a robust or a stochastic control problem. So here, there's kind of a lot going on the slide, but I'll walk through it plot by plot. So the top graph here is showing annual emissions, basically the rate of emissions. So in terms of units of gigatons per year, so billion metric tons per year. And the kind of left-hand side of the top graph is historical data, so real data. And the right-hand side is a couple of different scenarios in the future, kind of starting from today and going on to 2050, which is kind of the really crucial decades for climate action. So you can think of the emissions in the top plot here as basically our control input. We don't maybe have direct control over this in the same way that you'd have control over a valve position or an actuator position, but more or less with our policies and our choices, this is what we can control as humans. And then the blue curve looking ahead, this is kind of where we're at currently with international pledges from different nations. So you can see that we are at least hoping to stop increasing the rate of emissions and decrease it, but only very gradually. And then the bottom plot here, the sort of exponential approach towards 0, is a pathway that's compatible with 1.5 degrees Celsius of global mean surface temperature rise over pre-industrial levels. So this, roughly speaking, is what climate scientists tell us is what we need to do to avoid some really severe and potentially catastrophic impacts of climate change. So you can think of this as a control input, and then really the state of the system, the climate system, you can think of as just an integrator, so just the cumulative emissions over time. So all this plot is just the integral of the top plot. And then an output variable, if you like, is an observable or measured output would be the temperature rise in degrees Celsius that we have observed. We are currently around 1.3 to 1.4, somewhere in that range of sort of time average and spatially average temperature rise. Which may not sound too much, but if you compare it again to this 1.5 degrees Celsius threshold that climate scientists tell us, we're actually getting quite close to planetary boundaries there. And then, so these are basically the likely temperature rises that we would see from the emissions pathways that are sketched out in the top plot here. And so you can see in the blue, the sort of business as usual plot, temperature rise continues more or less linearly, even though we're sort of seeing a slight decrease in the emissions rate. And then the sort of clouded, shaded areas on the plot there represent uncertainty. So you can see that in the mapping from emissions to temperature rise, actually there is significant uncertainty. And this is a very simple model. Of course, true climate models are much more higher dimensional than this sort of scalar model, but it captures a lot of the sort of basic effects that we see in those higher fidelity climate models. And then the bottom plot here shows something like the impact of this temperature rise. Of course, we don't actually care about overheating. What we care about is the increased frequency and severity of things like droughts and wildfires and extreme weather events and the other manifold impacts that we would see of these temperature changes. So here, the uncertainty windows are enormous. And I think that's because we basically have no experience of what the Earth system is like under severe climate change. So if we're at 3 degrees or 4 degrees Celsius of climate change, which we're roughly on track for about 3 by the end of the century, we really have no idea what that looks like. So this is an issue of deep uncertainty, and the distributions themselves are uncertain. We don't know basically if this impact distribution is light-tailed or heavy-tailed, if it follows a normal distribution or a Pareto distribution or somewhere in between. So this anyway, is a problem with decision-making under deep uncertainty. So actually what the damage function looks like is not clear. It roughly might be polynomial in the temperature rise, but that degree of the polynomial, we don't know if it's quadratic or quartic or something higher than that. And we don't know what that coefficient A there is. And in fact, I would say that we don't even really know how to measure the damages, I think, especially in the extreme case. So what should the units on the y-axis there even be? Are we talking about impacts to all living creatures? Are we talking about impacts only to sentient beings, only to humans, only to some humans, right, within national borders or something like that? So I think it gets really more in the realm of philosophy to sort of understand how to specify what the problem should be there. But anyway, from a control theory perspective, you could imagine formulating this as something like an LQR, LQG type problem, where we want to minimize essentially the area under this curve, the cumulative impacts on whoever. And there's also some cost associated with reducing U. So there's sort of a control cost, an actuator cost, as well as an output cost. And you can imagine formulating that as an optimal control problem. And indeed, the Nobel Prize in Economics in 2018 was given to a guy named Bill Nordhaus, who works at Yale, who basically did that, more from an economics lens than a sort of LQR, LQG type lens, but quite similar. Okay, so you can see here that it's really the cumulative emissions. So this plot here is really what we care about, more so than the emissions rate. It's really the integral of the emissions rate. And so responsibility for causing climate change basically tracks more or less with the amount of cumulative historical emissions that we've put into the atmosphere. And the US, although we're only 4% of the world population, have emitted about 20% of the greenhouse gases, the cumulative greenhouse gases to date. So I would say, and not all people would agree, but I would argue that we have outsized responsibility to act quickly on climate change. I'm not the only one who feels that way. There was a study put out by the International Energy Agency, by no means a radical group, but they basically said, for that 1.5 degrees Celsius pathway, what is needed from different nations? And they broke that out into basically, using this sort of justice lens where they think about how much have we historically emitted, but also what is our capability to act? So you can imagine that a wealthy country like the United States has lots of capability, whereas an impoverished nation may not. So they basically argue that countries like the United States, advanced economies, need to reduce emissions by about 80% from 2022 levels by 2035, right? So think of this as roughly a decade to get roughly 80% emission cuts. Extremely ambitious. And then even developing countries are still in the kind of 60% emission reduction range, which is yeah, a lot. So here's what that looks like. This is United States emissions from all economic sectors. Again, in units of, I guess this is million, so megatons per year of carbon dioxide equivalent. That just means CO2, but also other greenhouse gases that can warm the climate. And so you can see that we're on a mild reduction trend, but to get that 80% reduction, we'd really need to speed up the rate of emissions reductions by about a factor of 5. It's quite a lot. And then if you break out by different economic sectors, this is the transportation sector. There's been mild progress on transportation, planes, trains, automobiles, but not quite as much as we've seen in the economy overall. The industrial sector has seen mild progress, and this is really due mainly to things like offshoring. So moving industrial manufacturing from the US to other countries like China and others. This is the agricultural sector, so you can see that that actually has been increasing. So not only do we need to speed up, but we also need to switch the direction of the trend here. And then buildings, which I work a lot on, also have not made much progress really in my lifetime. So emissions there are increasing. And I should note that this is the fuel that's burned directly in buildings. So this does not account for the electricity that's broken out into a separate economic sector. And this really is the success story of US decarbonization so far. So you can see that starting around the time of the peak here, around 2005, it was pretty weak, but you can see around 2005 we began a pretty impressive emission reduction in the power sector, and this is due in part to things like wind power and solar power ramping up, but also largely due to natural gas displacing coal for electricity generation, which is somewhat cleaner, although still a fossil fuel. So big idea here. Oh, sorry, did we have a question? Maybe that's someone online, but anyway, the big idea here is that we haven't seen much motion in most economic sectors except for electricity, which is where we've really been winning. So the idea of electrification is to kind of piggyback on that success from the power sector in other sectors, right? To switch over the sort of dirtier and more fossil fueled activities in those other sectors to electricity to kind of benefit from that success. So this kind of sketches out a two-step pathway for deep decarbonization, kind of on par with what we think is needed for international agreements. So the first step there is basically to, oh, sorry, let me explain what's on this plot. So this is, again, annual emissions. And I think this is as of 2022 or 2023, the most recent data I could find, but broken up by those 5 economic sectors that I showed previously. So you can see transportation is the largest emitter, followed by electricity, with the agricultural sector on the right-hand side there at the smallest contributor. So first step in here in the strategy is basically to clean up the grid. And we're already well on our way on that, although we need to speed up, but I think we're moving in that direction. And then the second step is to do electrification. And here I've broken that out into 2 stages. So this is electrifying private vehicles. So things like the cars and the trucks that people drive, not long haul trucking, not international freight or anything like that. But that reduces emissions by around another 16%, bringing the total up to about 40%. And then in addition to that, we can also electrify space heating, water heating, and some low temperature process heat in industrial processing. So things like making plastics, things that use hot water and steam in industrial plants. So there, if we can electrify all those things, we come up to about 61% reduction, which is not quite the 80% that we are looking for, but it does get us on track. And of course, there are other things that we could do on top of this. So there are things we can do, basically just eating healthy diets, eating the ways that our doctors recommend would reduce the emissions from the agricultural sector quite significantly. The main reason there is that we as Americans eat a lot more red meat than our doctors say that we probably should. But also you can imagine, buying less stuff or different stuff as kind of lowering this barrier. This is mostly the leftovers here is mostly cooking. So that also is not too hard to electrify. The reason that I didn't include that in this illustration here is that really the point I'm trying to make is that with this 2-step strategy, we can use essentially existing technologies that are economically viable to make deep and rapid progress on climate change. So the tech here is basically wind turbines, solar panels, batteries, pick whatever other clean electricity generation source you want. Maybe it's nuclear, maybe it's natural gas with carbon capture if we can get that working. Maybe it's geothermal, I'm not quite sure. But basically some mix of those clean generation technologies on the grid side. And then on the demand side, it's basically EVs and heat pumps is pretty much what I'm showing here. And a heat pump is just a really efficient machine that is powered by electricity and provides heating for various purposes. Okay, there's sort of an elephant in the room, which is that if we did this, not only would we need to clean out the grid, we need to build out the grid capacity by about a factor of somewhere between 2 and 3 in order to accommodate all the new demand that we're shifting from fossil fuel combustion over to electricity. And if we did that, we basically would increase the electricity demand peaks that we see quite significantly. So this is research results that one of my students produced recently. And here we simulated about around 5% of the US building stock, which is about 125 housing units. We simulated around 3 to 5 million, somewhere in there, but a representative sample from each county in the US. This is kind of the today scenario, sort of business as usual. And you can see that the peaks are highest in the Southwest, where it gets really hot and very sunny in the summers. And they peak around somewhere maybe 10 to 13 kW per household. And then this is the all-electric future, where everything is electrified, including space heating and vehicles and so on. And you can see that the peaks not only get much larger, so here the upper end of the heat map is more about double what it is over here, but also they shift from the south to the north in the country. So you see places like Minnesota, Michigan, also the Northeast, Maine, New Hampshire, and so on, North Dakota. We see really significant increases in peak demand on the grid there. So the basic question, at least that I'm interested in answering today and discussing with you guys today, is can we use better control methods to mitigate the impacts of these transitions toward electrification on the power grid, whether that be at the distribution scale, at the transmission scale, high voltage, or even the infrastructure within our homes and businesses. So that brings me to the first project here, and this was done in a test house that's just off of Purdue's campus where I work. We call it the DC, standing for direct current, not Washington, DC, the direct current nanogrid house. It's about kind of a typical single family home for the US. It's about 200 square meters or about 2,000 square feet of floor area. It was built about 100 years ago. So for our Indiana environment, we call it a historic building. I don't know if there are any Europeans or other folks in the room, but it's not exactly old by most country standards, but for us, it's pretty old. And we renovated it over the course of, I say we, it's me and also several other PIs at Purdue who've been working on this project longer than me, but renovated this house with new insulation, better air sealing, with different equipment for heating and cooling. So that includes an air source heat pump to provide both space heating and also space cooling. There's a battery in the basement. There are solar panels on the roof. We have an EV charging station, electric vehicles charging station, sorry. And really one of the novel things about the house is that we can switch the major appliances as well as the solar panels and the battery from kind of a conventional alternating current wiring system over to a direct current wiring system if we want to. We're not quite able yet to stably operate the DC nanogrid. Actually, the control of the power inverters there, or sorry, power converters ends up being quite challenging. And we can't just buy off-the-shelf components because DC nanogrids at sort of this lower voltage scale are not really a technology yet. So we're having to do some innovation on our own there. I'm not going to talk about that problem at all today, although it's quite interesting. I'll just talk about sort of the AC side, kind of conventional wiring, and really just looking at the control of the devices within the home in a more conventional context. So just as a contrast, like if you work on robotics, typically you can buy a robot that you can, reprogram and tinker with for, anyway, you can buy something off the shelf and usually for not that much money, tens of thousands of dollars. This test bed here, typically to buy a home in our area is somewhere around $250,000 to $500,000. And then we put a whole lot of effort into renovating it and deploying a lot of sensors. So this is, for me, a really interesting and exciting test bed, and not one that you can find in most places in the US. So within the home, 73% of the electricity use is actually for heating and cooling. So in our Indiana climate, we have both severe cold winters. I think it gets down Fahrenheit to maybe -5 in most years. And then it also gets really hot and sunny and humid in the summers. So it may not be the most friendly climate to live in, but it is a really good climate in which to do heating and cooling research. So I feel lucky in that respect. But about 3/4 of the energy in the house is used by the heat pump. So here, the blue wedge over here is the outdoor unit of the heat pump. This contains a rotating machine called a compressor, also a couple of fans. AHU stands for air handling unit. So this is the indoor distribution fan. And then this aux heat is just a resistor, basically, a heating element. And so if you add all those three up, you get about 75%. So that tells us that really the heating and cooling of the home is the main thing that we want to focus on when we're thinking about grid impacts, when we're thinking about reducing costs to homeowners for energy bills and things of that nature, also emissions. So We reviewed, as part of our first project on this, all the literature that had been done with real field experiments of heating and cooling equipment in residential buildings. We found 15 papers going back for maybe 25 years, the first one around the year 2000. And none of them actually studied the configuration which is most common for electrified homes in the US, which is to use an air source heat pump with backup electric resistance heat. So we thought, hey, we're the first people to attack this. And I'll tell you a little bit about how we approach that. I should say before I get into it that this is kind of almost like a hello world of control. So this experiment may not sound super sophisticated to you. We basically use model predictive control with a low order linear model and a convex objective function and convex constraints. And we used a time step that probably feels really slow. The thermal dynamics within a building typically have time constants on the order of maybe 3 to 10 hours, something like that. So our control time step was about 15 minutes here. And then we have a later follow-on project where we were considering faster dynamics, and we looked at maybe 30-second time steps. But compared to controlling power electronics or something like that, it's just a different time scale completely. Anyway, this is what the control system architecture looks like. So the red block here is the supervisory control system that we developed in this project. And you can see that it takes input data from multiple sources. The top block there really is just an internet connection. And from there, we download feedback from the occupants in the house. So if people are feeling too hot or too cold, they can notify us of that in a phone app. And then that loops into our control system. We also can download, for example, weather forecasts. We use those regularly, but we aren't really doing this currently, but we could download real-time electricity prices and other reliability services from the power grid that might have to do with perturbing power consumption about some nominal baseline. The control system also gets measurements. So it pulls indoor temperature measurements from the thermostat, basically, which is the same device that sends measurements to the device level control system. And then we also put in a power sensor. So we have circuit level electric power metering that we can get at sort of 1 second resolution. And we feed those measurements into the supervisory control system as well. And that was about $150 device, so not super expensive. And then we send basically our actuation signal is the indoor temperature set point. So this is what you would specify on a wall thermostat at your home. So we send that to the device level control system. The heat pump is a variable speed machine. So the device level manufacturer controls typically use PID with some saturation nonlinearities, rate limits, and things like that. So it imperfectly tracks the indoor temperature set point, but if we don't make huge sort of step adjustments, the tracking is usually pretty good. And because we're working at sort of 15-ish minute timescales, the tracking dynamics, the sort of faster transients from the device level control system tend to wash out. But we can model those, and in the second problem that I'll show, where we were working at faster timescales, we actually did model those sort of low-level dynamics. And then this device itself, this control system here basically tunes compressor speeds, fan speeds, so looking at RPMs of different motors and things like that. Okay, so one sort of innovation that we made here is sort of a simple way to get a control-oriented model, so a linear dynamical model of the thermal dynamics of a building. And we use an approach called thermal circuit modeling, which is really similar to RC circuit modeling in electrical engineering. So here the analogy basically is that voltage is like temperature and current is like heat flow. This approach is very old. So it goes back to before the age of digital computers. So if people wanted to simulate a building and understand maybe how big of a heater they needed to put into a building, they actually would build an analogous circuit, an analog circuit, and they would run it under the appropriate sort of boundary conditions and get estimates of how big components could be and things like that. We're not doing that, obviously, but it's just a tried and true approach. This doesn't capture all of thermodynamics. Of course, there are nonlinearities, things like thermal radiation exchange between surfaces, scale like the temperature to the 4th power. But over the relatively small temperature ranges that we're looking at, a linear model is pretty good. So the dynamics of this, you can basically apply Kirchhoff's laws and Ohm's law and get out a linear differential equation here. The blue highlighted parameters are things that we fit through actually a passive system identification process. So typically in sysid, what you would do is send out something like a pseudo-random binary input sequence, a bunch of step changes that you hold for random durations, basically. And then you would learn sort of transient response model from that. But here, actually, in most houses, or some houses anyway, people will actually do kind of a square wave temperature set point signal anyway. So a lot of people like to sleep a little cooler in their house overnight, or else they want to save energy by reducing temperature set points a bit overnight. And so they'll do a downward step response maybe at 10 p.m. or midnight. And then in the morning, they'll warm the house back up, say at 6 a.m. with another step change to the set point. So we basically get a bunch of step responses more or less for free. So our process for model fitting here, again, we gather passive observations and we only need about 1 month of data. And a typical smart thermostat, something like a Nest or an Ecobee, will store at least that much data on it. So it's not hard to gather that much data from a home. We approximate, oh, sorry, I should say here what the different driving signals are. So this is the outdoor temperature, T out. And then this is the indoor temperature, T is the thing that we control and also measure. Q dot here stands for heat transfer. So this current source here really is a heat transfer source for us. And subscript C here means controlled, and the subscript E here means exogenous. So the Q dot E controls or contains not only basically modeling errors, it's sort of a conventional disturbance, but it also includes things like the heat gain from lights, from electronics, from body heat, and also from sunshine that hits the space. So basically, the C's play and R's play the same role that they would in electrical circuits. And then this Tm here is the mass, the temperature of the thermal mass, the sort of deeper thermal mass in a building. So if you think about this room, there are kind of two types of energy storage or heat storage elements. And one is the air that's in the room. And so that's really what this capacitor C represents. And then another one really is the deeper thermal mass of the room. So things like the construction materials in the furniture and the floors, things like that. The time constant that typically associated with the indoor temperature change, the air temperature change, might be on the order of hours, maybe 1 to 2 hours. And time constants for thermal mass and typically are on the order of tens of hours. And so we do kind of a 2 time scale thing here where we approximate the mass temperature as roughly constant and we focus on the air temperature dynamics instead. But you can easily change this voltage source here to a capacitor as well and do some model-based estimation to figure out what that C should. It's a challenge because the mass temperature is typically not measured. We have wall thermostats that measure air temperatures, but we don't typically measure the floor temperatures. Yes.
And wouldn't the mass temperature really not be an exogenous variable, but really be an effect of or a consequence of T out and probably should be its own state?
Absolutely. Yeah. So the question for folks online who may not have heard that was, shouldn't the mass temperature really be more of a state variable than an exogenous variable? And yeah, that's right. And so we use this kind of 2 time scale approximation, basically saying that the mass temperature dynamics are slow compared to the air temperature dynamics. And so we model them as approximately constant. Although, yeah, a better model would include dynamics on the mass temperature as well. And then you'd run something like a Kalman filter to estimate it, even though it's unmeasured. That's a good point. Thank you. By the way, if other people have questions, please feel free to just raise your hand. Okay, so we gather roughly a month worth of passive observations, which do include some of these step changes. And then we approximate the mass temperature as constant, and we just use the time average indoor air temperature. The idea being that, if this mass stuff is in contact or thermal contact with the air, it'll tend to sort of roughly be on average about equal to the air temperature. We then fit the outdoor thermal resistance to we select for particular periods when a lot of stuff is equal to 0 in the dynamic equation that I showed earlier. So we can just do kind of a direct fit using linear regression to back out the thermal resistance between the indoor air and the outdoor air. And then similarly, we use data when this disturbance term is likely very small. We look at the step change data, step response data, basically that happens overnight in order to estimate the other 2 parameters, the resistance between the indoor air and the thermal mass, and then the thermal capacitance of the air, so the energy storage capacitance. And then now we have everything basically that shows up in this equation except for this kind of catch-all disturbance term here, which includes some physical effects, but also includes kind of all the unmodeled dynamics. And so we form a training data set on that Q dot E, and then basically we are off to the races with a supervised learning problem. So we do kind of the traditional workflow in supervised learning. We split our data set into some training and validation data. And then we tried out a range of models. We do a model selection process and then hyperparameter tuning and so forth. And we ended up using a support vector machine for this time series regression problem. It ended up working the best of the things that we tried. And so here I'm showing our predictions of the indoor temperature, and this is all training data, and this is unseen validation data here. You can see we have about 1 month of training data on the left and about 2 weeks of validation data on the right. So the temperature predictions are pretty good. I wouldn't say that they're amazing, but they're basically good enough for control purposes. And then over here, this is basically the same model used, basically conditioned on having an accurate estimate of the indoor temperature. We then try to predict the thermal power, basically the amount of heat or cooling that's produced by the heating or air conditioning system. And our predictions on that also end up being pretty good. I wouldn't say that they're amazing, but again, good enough for most control purposes. So now that we've arrived at a model, and again, this is kind of a hello world of control. This is not the end all or be all of what we could do in the test house, and we're working on other models as well. But we use basically a certainty equivalent linear convex MPC formulation. So here our decision variable is the indoor temperature trajectory of the set points that we will send to the low-level control system. So those are denoted T1 through TK. This is the prediction horizon here, which we use 1 day as the prediction horizon. And then also decision variables. These are variables that get fixed by quality constraints, but they're unknown at the beginning of the optimization problem, are the thermal power that's produced, again, the heater cooling that's delivered to the building, and then the electrical power input to the heating and cooling equipment. And we want to minimize a weighted sum of 3 objectives. These include the energy cost over the prediction horizon. That's the first term, also the peak power demand cost. And the reason we want to penalize that basically is that impacts on things like the power grid typically scale with the peak demand. Actually, system-wide peak demand or component-level peak demand is usually the criterion that we care about, but the demand at the sort of household level is usually pretty well correlated with that kind of system-level demand. And so we penalize it at the device level. And then the last thing we have is essentially a tracking error penalty. So here we're using an L1 norm, roughly tracking error penalty. So R would be what we view as sort of the user's temperature preference. And then T is what we actually deliver. We penalize that in absolute value sense and then add it up over the prediction horizon. And I should say that these prices here are time varying. The energy price that shows up here, this is actually a constant. It doesn't have to be, but in our formulation it was, because we pay just one price for electricity, about 14 cents per kilowatt hour. And we pay that no matter what the time of day is or what season of the year it is in our test house. But you could easily put in dynamic pricing related, for example, to wholesale electricity prices and get some load shifting potential from the heating and cooling equipment, basically doing something like a buy low, sell high type approach on that time varying price signal. But for the thermal comfort price here, we do say that this is time varying. And the idea there is that when people are asleep, they're probably more sensitive, or sorry, less sensitive to temperature changes than, for example, in the early morning when the house is a little cool, you're just waking up. I think you want a nice, cozy house at that point. So we penalize deviations at a higher price at those times. The constraints are the linear thermodynamics that I showed earlier. We also have equipment models, data-driven equipment models that we learn essentially from manufacturer spec sheets and data. And then we have capacity constraints. So the heat pump can only produce so much power. Also, it can't switch easily between heating and cooling. So the thermal power that we provide can't go negative. And then we have comfort constraints. So in addition to this kind of soft tracking error here, penalty, we also have a hard constraint on the temperature deviations from the preference. And then we have lots of input data here. And I guess if we were to characterize, like in a block diagram, what the actual state is that this control block would take as an input, it would include not only the temperature measurement from inside the building, but it would also include a vector forecast of outdoor weather conditions, specifically the outdoor temperature. And then also it would take in basically our predictions of the disturbance. And those basically we make based on the weather conditions and the time of day. Those are our predictive features. And then we have the model parameters also kind of embedded in the optimization. So here is kind of one interesting day. In the top plot here, I'm showing the electric power. In the middle plot here, we have the indoor air temperature, and the bottom plot here is the outdoor air temperature. And the red curves here are kind of our baseline control, and the blue curves here are under our supervisory predictive control system. And then in the middle plot, the dashed curves are the actual measurements that we're getting from the thermostat, and the red curves are the set points that we're sending out. So you can see here that the device level control system tracks the actual set point, but typically with an offset of about 1 degree Celsius or about 2 degrees Fahrenheit. So it has, if you like, a steady state error term. Nothing really we can do about that. That's kind of the manufacturer controls. And you can see that the weather conditions under kind of our baseline day, the red day, are a little bit warmer than they were under the MPC day. So this is a more challenging control problem for the predictive control than it is for the baseline control. The spikes up here in the electric power going up to 24 kilowatts. Does anybody want to guess what those are?
Your thermostat switching between.
It's not thermostat switching. That's a good guess. It's not EV charging or something like that. It's another good guess. So what this is the backup electric resistance heat turning on in this weirdly periodic fashion. And the reason it does that is because a heat pump, basically, it circulates a refrigerant through an outdoor heat exchanger. A very cold refrigerant flows outside, and that absorbs energy from the outdoor air. Even when the outdoor air is quite cool, the super cold refrigerant sucks heat out of it, basically. But when that happens, even very cold air has some moisture content in it, and it basically condenses on that coil and then freezes, and you get ice buildup on that component. And that reduces the rate at which it can absorb energy from the outdoor air, and it makes the capacity for heating tail off, basically. So in order to avoid losing the capability to provide good heat to the house, what manufacturers do is they periodically basically reverse the direction of refrigerant flow. So they send super hot refrigerant out through the outdoor unit to melt off all of that ice. And so that's what these big spikes are here. And we're still getting those big spikes here, but actually we're running the heat pump a little bit colder overnight. And the reason for this is that we basically have a lower price for the thermal discomfort to the occupants in the overnight hours here. So this is basically between midnight and 9 a.m. So because of that, we don't get quite the same spikes for defrost usage. We don't get quite as much ice building up on the outdoor coil. So this effect of frost buildup, it was not at all on our radar when we started this problem, but it ended up being one of the dominant effects, both for this problem and for the next one that I'll discuss. Anyway, so on this day, we basically saved somewhere around 13% energy, I think, even though it was somewhat colder outside. Now, you might just say, well, okay, but that's because you kept the house colder overnight. And I think that's a legitimate criticism. So here's another day where we compared basically to a night temperature adjustment. So here we start at midnight, different time scale. I'm not sure why exactly, but we start at midnight here and then end at the next midnight. So this is one day. And you can see in the indoor temperature profile here, it's lower overnight and higher during the day. And here, I guess it's not really a fair comparison because we're keeping the house somewhat colder, actually an offset of about 2 degrees Celsius or about 4 degrees Fahrenheit, which is pretty significant. So I don't think we want to declare victory based on sort of that indoor temperature difference. But it is worth noting that when we get this step change in the set point, I guess my laser pointer sucks here, but around 6 a.m. we do a step from 20 Celsius up to 22, or about 70 Fahrenheit up to about 74. And when that happens, the low-level controller on the heat pump basically freaks out. It thinks that it has run out of thermal capacity, and it says, oh no, we need to turn on this backup electric resistance heating element in order to keep the house warm. And so for that reason, we see a spike in the electric power usage in the morning with a bit of a time shift, basically because of the delays built into the manufacturer controls. So I think on this day, the energy savings were more significant, but I'm not going to report that number because, again, I don't think it's a fair comparison due to the basic temperature difference inside. The main thing is that we avoid this big spike in power consumption in the morning by doing a slow, kind of gradual ramp up rather than a sudden step change. Now, you could, I think, legitimately argue that you don't need model predictive control to tell you not to do that. I think a simple heuristic that just kind of spreads out that step change into, say, 3 or 4 hours could achieve the same results, and I think that's probably right. And actually, we've been talking with some manufacturers about just adding that to their kind of baseline thermostat controls. Okay, so the overall punchline here is that, again, with this fairly simple objective of just keeping people comfortable and reducing energy costs, we save somewhere between 20 and 30% of the energy bills over a 1-month testing period. And we did similar experiments for 1 month in the cooling season and found kind of similar reductions in energy use. So here, this is the outdoor temperature daily average over the testing periods. And it's actually the temperature difference between the indoors and the outdoors. And then on the vertical axis here, I'm showing the daily electrical energy input to the heating plant, which includes the fans and the compressor, as well as the electric resistance backup heat. And you can see that the trend line for MPC is significantly below the trend line for the baseline controls. So for our test house, that ended up being somewhere between $350 and $500 for the year, including both the air conditioning savings in the summer and the heating savings in the winter. Okay, so that's one problem. I'll talk about another problem here, which is about protecting electrical infrastructure within the house. And the idea here is that we want to protect not only the sort of circuit breaker panel that you might find in the basement of your house, but also what's called the service coming from the distribution grid into the house, which is basically the wires that connect the power grid to your home. If you use a lot of electricity, you need thick wires basically coming into your house so that those wires don't risk overheating. So you can imagine as you add a bunch of new devices to a house, you add more electrical demand, and you basically would need to upsize some of those components. And so here we're trying to do a control problem where we avoid that upsizing. So just for kind of a scale of the problem here, this is distribution. This is from an EPRI report. This is distribution of electrical panel and service ratings in different regions of the United States. And the thing that we're really interested in is how many people have small panels. So say below 100 or 150 amps. Typically, a modern house will be constructed with about 200 amp electrical service or maybe above, maybe 300 or 400 amps. And that's to accommodate things like electric vehicle charging, electric heating, and things of that nature. So you can see that there's a non-trivial amount in each of these regions, and in particular, the colder regions, the Midwest and the Northeast. There's a fair amount of homes, about 32% in the Northeast and 40% in the Midwest, that have quite small electrical panels. And so if those households want to switch from fossil fuels over to electricity, they may need to upgrade that infrastructure. And so the control problem that we're sort of posing here is, can we avoid those infrastructure upgrades by better sort of interleaving the operation of different devices within the house? So this is kind of, I guess I won't go into too much detail here, but there are many millions of panel upgrades that could be required. It's not hard to count into the billions of dollars, basically money on the table for avoiding these upgrades through advanced control. So significant monetary opportunity, I think, if we can figure it out. I won't talk too much about the methodology here because it's quite similar to the methodology in the previous problem that I presented. The main difference is that we added another control input. So we have actuation authority over the water heater as well as the space heating and cooling. And then we added another layer in our control hierarchy. So we still down here have the manufacturer controls. We still have our supervisory control layer. But now we added an intermediate control layer, which just does sort of rule-based control logic, if-then type logic. And that basically was an added layer that we found was necessary for robustness. We also moved to a faster 5-minute time step here, 30-second time step down here. And we're only looking ahead 12 hours, basically for computational reasons, that we only had a couple of minutes to make these decisions. And we ended up solving a mixed integer convex program rather than just a sort of continuous convex program. So those are computationally significantly more expensive. So I'll just jump straight to results, basically. So here we're comparing 2 days. One is a baseline testing day. This is the outdoor temperature. The other is kind of our control system testing here. And the middle plot here is the indoor temperature. So you see we're comparing to just a sort of constant indoor temperature set point in the business as usual case. And then the signal here that we're sending out, the actuator signal, is a lot weirder than it was in the previous problem where things were kind of smooth and even. And part of that is because we're using a faster time step. Part of it is because we're using an integer programming framework. And sometimes we have to do like a stop before we get to a full global solution there because we've run out of compute time, basically. So the decisions are sometimes suboptimal and there's a little bit of jitter. But also we're just solving a harder problem. So you can see that, for example, sometimes we lower the thermostat really far and really fast. And basically what's happening there is that there is defrost needed. So again, ice is built up on the outdoor unit and the manufacturer controls want to basically turn on the resistance heating element and switch the direction of refrigerant flow, which uses a ton of power. So basically to make room for that, we turn down the amount of heat that we're asking for. So that's what these large drops are here. And the bottom plot here, rather than power, I'm plotting the whole home current. So this is not just the devices that we're controlling, the heater and the water heater, but it's also kind of everything else in the house. And you can see that while this thing, the baseline control sometimes gets up around 120 amps for our house, on this day at least, we maintained the house below about 90 amps. And this is what the results look like over the full testing period. So this is 1 month from, I think, winter of 2022 to 23, where it got very cold in this early January period. And so that's the outdoor temperature is the black signal here. That corresponds to the right-hand y-axis. And then the scatter here is basically whole home current. And you can see that it's often above 100 amps and sometimes is above about 120 amps, which is enough that it would trigger circuit breaker tripping in the house and basically shut down all power to the home, which would be really problematic for someone, especially in the middle of winter when they have electric heat. And this is the testing period, same graph. And again, the black is the outdoor temperature. You can see that we got lucky basically and caught a super cold snap. I'm probably the only person in Indiana who was like praying for the coldest possible day in the middle of January, but we got one. And so we got good data there as well. And you can see that almost always we robustly maintain the temperature or the current below 100 amps, although there was this one 5-minute period where we went slightly above. And I think this is not a huge issue because it turns out, like if you look into the details of what makes circuit breaker panels trip, there are two mechanisms. One is a magnetic tripping, and there it looks at really fast time scale, fractions of a second type currents. So a sudden surge for a microsecond can trigger a magnetic trip. But usually those only happen when you're, several times higher than the rated limit. So if your limit is 100 amps, it might trip if you're at 200 or 300 or 400 amps. So we're at no risk of magnetic tripping here, but there is a thermal tripping mechanism where basically a piece of metal gets too hot and then it trips a switch in that way. And so a sustained excess over 100 amps could cause thermal tripping, but we think for 5 minutes it probably would have been okay. We did fix this. So I think this, you might ask, was just the sort of real-time control layer, the if-then logic that just kind of turns things off if you get too close to the 100 amp limit. You might ask whether that control layer was enough, whether we really needed all this kind of sophisticated machine for the MPC. And we found here that the reason that this failed, basically our real-time control layer would check if we're getting really close to 100 amps, it basically would start turning things down and eventually off the closer that we got to violating that constraint. And that basically had no predictive logic in it. So it also had a comfort constraint that said, if the water temperature in the water heater gets too cold, then you must run it, basically. And so we got this kind of conflict in our logic. On the one hand, we wanted to keep the whole home current below 100 amps. On the other hand, we wanted to keep people comfortable. And our logic basically said, well, comfort rules. And so that's what happened with this spike. And we fixed it basically by making some updates in the control logic beyond here that said, look ahead further and make better predictions of when people are going to take showers so that we can preheat the water tank to have plenty of capacity and to get through basically the early morning periods, which is when this happened. Anyways, I don't know that that's justification for needing all the complicated machinery of predictive control, but it certainly means that you need some anticipative type logic in the control system. And then this is basically the same data, but just showed as a box and whisker plot. So here, the red lines are the medians. This is the interquartile range. And I think these are the 2.5 and 97.5 percentiles. So everything above here is outliers, basically. And so you can see that the distribution, the tail ends more or less at 100 amps, aside from this one outlier, whereas over here, the tail is a little heavier and extends well into the failure region for a panel. Okay, so the upshot of this is basically, oh, yes, question.
Do electrical codes currently allow this problem to be solved with controls?
It's a good question. So for those online who may not have heard, it's do electrical codes allow for controls to solve this problem rather than hardware interventions? And the answer is we don't know of any devices that are currently doing this and approved in the field, but there is a provision in the National Electrical Code that says that you can use software to basically take the place of a current limiting device. And we found this after doing the experiments, but they require that you basically lower the limit to 80% of the panel rating. So rather than shooting for 100 amps, we would have to shoot for 80 amps, which we really exceed that significantly. So we think probably with better control and some better logic, we could actually knock this distribution down below 80 amps. But yeah, this I think would not be sellable. So about 10 minutes left. I think I'll just stop. I'll talk about this really quickly. So just two future-looking things. We have a proposal out that basically would do coordination between homes. So everything I talked about today was sort of within one building, but lots of people, including Professor Matthew here, have worked on coordinating lots of devices across lots of different buildings to provide services to the power grid more broadly. And so we have a proposal out basically for this DOE Connected Communities call with a couple of manufacturers. But here we propose basically a distributed optimization or control framework where there is, first of all, we have devices in a number of different houses. These are homes. This is called a home energy management system, basically the stuff that I talked about today. And then there would be a second control layer, or yet another control layer kind of at the grid scale, which is trying to basically communicate with all these home energy management systems to sort of harmonize grid level objectives, like, for example, protecting a transformer or a power line, with the building level objectives, like saving money on energy bills. And so I think really the interaction between these two control layers is quite interesting. So how do we come up with a distributed control framework that's good both locally and also globally? So that's one, I think, interesting direction. See if that gets funded. And then a second one here, this is a large proposal that involves University of Michigan as well as Purdue as the PIs. But this is around sort of next generation factory built housing. And the idea here is that most housing today is built with hammers and boards and people swinging hammers in the field. That's pretty slow and pretty expensive. We need to build a lot more housing, basically to alleviate the rising costs of housing that a lot of people are struggling with. And so if we could build housing a lot faster by making components in the factory rather than in the field, we could save people a lot of money. I think from a control perspective, also, I think it would be really interesting to see, if we can put new sensors, new actuators, maybe new equipment into homes and build it in on the factory floor fairly cost effectively, rather than trying to retrofit them in existing buildings. That might open up some new opportunities for control. So I think we'll stop there. And I'd just like to thank my collaborators and my students. Elias Pergantis here is a PhD student at the top left. He did most of the controls work here. And he just actually will graduate in a couple of weeks here. And then these are other graduate and undergraduate students who are on that team. And then the system level modeling stuff that I showed, Priya Darshan, my PhD student, led that. And it was done in collaboration with Sophia, our undergraduate, and then two professors. Some of you may know Kyrie Baker at CU Boulder and Constance Crozier at Georgia Tech. So I'd like to thank them all, and here's some references to the papers that I talked about today. I didn't take a ton of time for questions, but I'd love to take a few if anybody has. Yes?
So for the panel control thing, how does it account for like the other electric loads in the house? Like, what would happen if like the water heater's on full blast?
Yeah, it's a great question. For those online who might not have heard, it's basically in the panel protection problem. How did we account for other devices? So what happens if the water heater is running full blast and then somebody also wants to boil water for tea or run a blow dryer or something like that? The answer is that we sort of treated all that stuff as disturbances, and we came up with predictive models to try to, in our MPC formulation, to try to predict when people were going to use a lot of current. And we use basically quantile regression. So rather than trying to predict kind of the mean of that distribution, we try to predict something like a worst case realization of that, so that we could be kind of robust to very bad realizations of those current draws. So that's one approach. And then the other was that faster control layer. I maybe should have spent a little bit more time talking about that logic, but basically it in real time monitored the current from those other things as well as from the things that we control. And so if we saw a spike in current from other stuff, for example, the electric vehicle charging, which we didn't control in these experiments, then yeah, basically we would turn down or turn off the water heater first. And then if that wasn't enough, we would turn down the temperature set point for the space heating, and then eventually just like turn off the space heating. Does that make sense?
Mm-hmm. Yeah.
Good question. Thank you. Yes?
So for that second problem of like limiting demand, total current load, was the house battery integrated into that solution at all?
Yeah, it was not. So the question was, did we control the battery in the second problem? And the answer is no. The reason for that basically is, yeah, I mean, it would like make that problem super easy, right? But most people don't have batteries in their houses, at least today. And we wanted a solution that's kind of scalable for normal-ish houses. But yeah, certainly the battery control is interesting. Yes.
For the residential heating, how do the pre-electrification costs compared to the post-electrification costs? The savings you mentioned, they compensate for that?
Yeah, okay, so not so much talking about the control, but just like the equipment configuration. So we went from natural gas, space heating, and water heating and cooking over to all electric. How did the cost to consumers compare? I think it actually, for our area, I think they went up. And the reason for that is that we have very cheap natural gas in Indiana. But it's a little hard. We don't really have an A/B comparison on that because when we renovated the equipment over to all electric, we also insulated the house and reduced the air conditioning and heating demand a lot. But we've done some modeling on that, and there are good papers about that have kind of looked at that geographically throughout the US and Europe and other regions as well. And in most places, it ends up being kind of a wash. And some places you save a lot by electrifying. So for example, in rural areas where you don't have natural gas service, but you use maybe propane or heating oil or electric resistance heat. So there, if you can replace with a heat pump, then it saves quite a bit of money and emissions. But the comparison natural gas versus electric right now is kind of a wash.
I'm not sure if you mentioned this and I just missed it. How are the houses how is the house being used during the testing period?
Yeah, how was the house being used? Thanks, that's a good question. It was occupied by grad students. Grad student guinea pigs, basically. Not the ones who were doing the research, but other grad students in our lab. So, which is a little bit of an issue potentially, right? So I said that like, oh, we had this occupant comfort feedback in the control system, and if people were uncomfortable, they could report, but I think that might have been biased a little bit by the fact that like the people living in the house knew that their friends like publication and thesis and graduation. I didn't know what they said, so there may have been some bias there. We did other things to kind of quantify comfort, and it seemed okay. Any question? Okay, did we have any questions online? I guess, yeah, we had a question, does inflation factor in to have $1 billion disaster? Oh, this is an older question here. But to have $1 billion disaster, you need $1 billion infrastructure to be damaged. So first of all, for inflation, that first plot that I showed, and this is going back to slide number 1, I guess. That first plot is inflation adjusted. And so yeah, it does account for inflation here. But you're right that the value of the assets that are around to be affected does certainly influence this. So in a nation like the US, which has fairly well-developed infrastructure, there's a lot at risk. In a place that's more spread out, lower population, or not quite as developed, I think lower. And then Purdue alumni says, how long has the DC nanogrid house been around, and did it start before or after the Renew House? It's been around about 7 or 8 years. It started after the Renew House. Renew House stands for renovation for net zero energy wastewater, and that's all. And it's another test house that's right next door to the DC nanogrid house, and it's owned and run by Whirlpool Corporation. But I also do some work there, and it's kind of interesting from the multi-home coordination problem that I talked about at the very end. 2 is maybe not a large aggregation of houses, but it's more than 1. So we'd like to do some coordination between the 2 houses. And I should say that my colleagues, Eckhard Grohl and Davide Ziviani, were involved in the DC house renovation, that project for years before I joined Purdue. So I'm really piggybacking on a lot of the work and success that they did. Any other questions? All right, well, thank you all again for your time and attention.
Because it's Nejmier. Shows that you are. Obviously, that's not true. She never responded. What that's doing there.
When a group is so big that at least one person is one of those. Please.
With Johanna. It's like, and we didn't have any I've actually never taken it in class exam. Mine were COVID or even because I took the marketing class during the class. Yeah, I saw you. So yeah, that class was in person, but the exam was still take home. So I've never taken it.
I've got to make sure that it's not taken. That's silly and Christine explained. Here's a
Like that. classroom, so it's just like, so we have stuff that I work with a lot. They enjoy their class, found it really interesting. So that exam was really fun. There were certainly other classes that I did.
They follow a schedule.
This was a in-class exam, because like, I guess the thing is, they don't expect you, if it is a take home, they don't expect you to finish it in 2 hours. They give you 24 hours to do it or whatever. But like 560 for a 24-hour exams, and I'm just like, it's literally like some of those exams, I think we spent like 11 hours. I'm so fortunate if you can get money from other departments.
This problem. Part of this is just showing like how many.
We have something.
I'm really good at negotiating.
But I can't, otherwise we're just gonna have.
Really late every night,
That-
like
yeah.
that, and then I would jet lag, so I couldn't sleep in. So I.
Oh, hey, nice to meet you. Really great talking. My name is Jane. I'm a so tired.
But,
Yeah.
don't worry
So
about
actually,
chapter
I'm
that's
something control.
does that I haven't given you
So
feedback.
like
I will tell you
chat,
how many, but it's not
and
published.
we didn't come up with, I know you're doing.
You just need to get to other things, that's like, there's always risks, so you need to think about like, what can you,
Why not?
do and what you
Yeah.
have.
There's people to work out, just see all the data and, okay, this is great,
Yeah,
right?
for some parts, because I think my colleague was assuming, like, I mean, it's been done already.
Anyways, like, it doesn't give
Right.
you all the work. You need
Well,
help.
it's a simpler method of identifying RACs and
It's,
So you're
yeah, I
saying
have
keep-
colleagues who are.
the temperature is so
I actually almost put it
constant that the
aside.
suture.
I think it's a good question. Actually, we're collaborating right now.
Because that might be a path that you could do if this other, although our indirect temperatures might change, or you have to because they change.
How much data
They
we need.
wanna have something all the time, so that the TDOS term, the inside temperature is yours.
You don't
Battery
need
is multiplied by.
Right, yes.
It's not the temperature, I think.
Yes,
temperature
because
is-
likely it is hidden on.
I know, it's not gonna be perfect, but
Like,
none of
yeah.
this is working in my way, so maybe that's.
Yeah, that's the, yeah, I think, yeah, like you mentioned, it's just the. I just assume like
In reality.
a little bit of wrong assumption of what we had with data, like with this and then.
I think you should have.
So I mean, when I say good data, I mean. Yes, because the problem was the timestamp, for example.
Actually, so you're-
So the different time zones in the joint.
Yeah.
And what's point, like 5 hours, like.
Yeah.
So I guess-
It's a good point, like.
Just
you got them
add,
different-
So I'm trying, what I'm trying to.
I was like, okay, maybe like.
What,
that
yeah,
might-
why is it better? And so you need to think
I'm not
about
saying-
how you,
I was
as a,
saying
you know,
that-
because maybe the
So,
chapter
like,
is about
there might be
literature.
a-
And then the analysis of different models have more qualitative
So,
things,
yeah.
and a recommendation.
Yeah, that's what
And then
I'm
you
talking
keep working over the years to try to get you. So it needs to, that's why I
It needs
was.
to be polished
It's
and look
still on.
it's versus, I know it's.
It's just feel like we're still working on it. So that's not acceptable. So that's why I was like, then you figure that part out, but you can get there.
Yes.
So, yeah.
Right, I'll let you later.
Have it-
So you gotta predict the color.
I assume you find the least.
You still have a model. You already done the work to the model.
Being a political person.
So like.
Another person asking,
It's
can be done.
It's not gonna have a log error. I think there. you could
Email gas like that.
And actually, what you care about isn't so much the model.
Research incentive, I have something like 90K my research incentive, I did a postdoc.
If you do it like a transfer words,
I cannot even like
just do it on this building.
minus something in my research.
Yeah.
It's basically just like, reduce temperature as much as comfortable. When people complain and reasons. So I think RL can absolutely discover problems on it first of all. The second problem, I think, maybe not, most challenging. And then you can actually have complex problems that involve time varying prices. And
Yeah,
complexities.
yeah.
And there, I think, yeah.
Right, I mean, and he doesn't really know.
Or yeah, so you're saying very like very little. And that's actually one of my doing that.
Oh, really? Yeah. So I think that's.
Well, to do things that, you know,
Well, they have this building for you to just.
set precedents, which would be.
Yeah, okay, so, but I actually, so I'm joining university. I worked, like, my application, people are energy, related things, like, I think. Yeah, I don't know if they know coding, that's the project I worked. Teaching these. Yeah, maybe I'll give an email. Yeah, definitely. Me too.
Because like I would never be eligible for a teaching release in my life.
People there.
So do you know where the value speaking there?
Yes.
Okay,
I
so
was for years, I was hiring a bunch of people and always saying, oh, we gotta get a teacher release. And I always said, no, because.
when do you plan to try to actually?
Thanksgiving probably, yeah.
It wouldn't necessarily be like.
And that was.
Yeah, actually, I can send you the address. That's like a file.
You mentioned that.
Teaching release and if I keep try to
Yeah, so I'll have our. So I think the collaborator who's an expert on that stuff. So basically, what we would like to do is have that kind of battery and at least one of the major appliances. We're thinking of heat pump because it's the big one that has some DC motor on
Maybe,
DC battery charging.
maybe,
And we'd like to be sort of grid connected.
yeah. Well, that's, I mean, I guess talking to Indiana is going over Jeff's head. But, yeah, I talked to Jeff.
And the other one.
Maybe let you bounce it up to me, yeah. I don't know.
Basically, we need solar inverter and then another one would live.
Are you joining us at tea?
Yes, okay, but I need to send this email. Okay.
How all of those inverters should work and they might fight each other.
There's.
You have ones for conforming, the other for following, there's some bad or here.
Has like.
That's what's gonna happen. Will the voltage be stable? or not?
Syria.
And then also like, I think the typical way people do off grid.
Oh, yes.
Grid.
It's fancier. I mean, like they try to say modern looking coffee shops. Yeah, it used to be like very.
And so then you're sort of charging and discharging the battery only for bus stabilization. And we also want to be able to like, excess solar power. Or maybe they don't have excess solar power, we want to push that. So, short answer is like, we talked chapter around, we did want to design this for something, we just wanted to ask and it haven't worked. And we just haven't been. DC converters for voltages and powers this level. So I think you can find some of these components, but for like industrial scale, higher voltage.
That's sort of why, I guess.
Yeah, so we're kind of in the order 1 to 10 kV.
Vicor has bus modules.
Vicor?
Vicor, VICOR. They're a good company. We used some of their stuff for, I'm on the formula team here as well, so like our DC-DC converter is sort of like a Cascade 600 to 12, but they make, yeah, like the BCM family of products, like these bricks that are half to 1.5 kilowatt. they support like PM bus protocol, which is like an I²C thing. You can have multiples on the same thing. You can parallel them really nicely. There are options there.
Interesting. Yeah, we did not know about this company. We looked at a couple of others, but not this one. So.
Yeah. I don't know if they'll have exactly what you're looking for, but hopefully it's something.
Yeah, so if you shoot me an email about both of these things, the house and also these power electronics, I think that would be super helpful. And I may connect you with one of my students or else with my colleague.
Okay.
My
All right,
Yeah,
then I
that's-
can get your email from Matthew.
or if you just search my last name, Kircher.
Okay.
Actually, my email is my last name. So yeah. All right. But yeah, no, thank you. That's super helpful.
Yeah, of course. Thank you for the presentation.
Okay, have a good weekend.
Too.
Oh, yeah. Sorry to like keep you so long.
It's fun. I love all the questions.
Sorry, I say cool talk. I'm a relatively new faculty here in controls,
Which department are you?
here in electrical engineering. Yeah. So I'm in systems and controls. I was curious because so I've done a bit of work on distributed MPC, so I was wondering like what models are you looking at for when you talk about like the multi-house case, and what sorts of application challenges? Because I think it's really cool that you're actually applying your algorithms to the real world, right? And that comes up like some challenges that you